Okay, now that we found the first derivative and the second derivative, the first thing we need to do is take a look at the first derivative. So recall that we want to be able to find the critical numbers. Okay, so if we want to find the critical numbers, okay, that means when we set f prime of x equal to 0. Okay, so when we look at this, okay, we have a numerator and denominator here. So if we take a look at 4 minus x, we're going to set that equal to 0. And solving for x is going to give us 4. So that's one of the critical numbers. Now, if we also take a look at the denominator, this is x to the 1/3 times 6 minus x to the 2/3, and set that equal to 0. Now keep in mind that this is a restriction. So these values would not exist, but we still need to figure out what are those critical numbers. So that means we're going to have x to the 1/3, which is equal to 0, or 6 minus x to the 2/3. And again, that's when it's not equal to 0. So that means that if we took the reciprocal and raised both sides to 3/1, then x is going to equal 0. Or over here, we can raise it to the reciprocal. So we get 6 minus x, which is equal to 0. Negative x is equal to negative 6. And so x is equal to 6. So, okay, keep in mind here, and then we're going to write this out, that we know that f prime of x is equal to 0 when x is equal to 4, and f prime of x does not exist when x is equal to 0 or 6. But we do know that the critical numbers are 0, 4, and 6. So let's go ahead and draw our number line. We know we have 0, we have 4, and then we have 6. Going from negative infinity to positive infinity. So here we have now 4 regions. So 1, 2, 3, and then 4. Okay, so what do we know? Well, we know that we have this interval that goes from negative infinity to 0. Okay, the second interval goes from 0 to 4. The third interval goes from 4 to 6. And the last interval goes from 6 to infinity. So what we want to do is we want to check, okay, what happens when x is less than 0. So for region 1, if we pick x to equal, let's say negative 1, okay, let's go ahead and plug that in. So if you want to make your calculation a little bit easier, okay, my suggestion is maybe just use Desmos and then create a table. So you can go this route if you want. You can do it by hand. I'm going to create a table. Okay, so we have x1. And then here, I'm going to write in our formula. Okay, so our formula is our derivative function. So it's going to be in the numerator 4 minus x1, right? And then we're going to divide that by x to the power of 1/3. Okay, and that is times 6 minus x1 to the power of 2/3. Okay, and then I want to make sure that this also has an x1. Okay, So now let's go ahead and put in -1. We're going to choose -1 into region number 1. So we're going to select -1, and we can see that we get a negative answer. Okay, and so then we know that it's going to be negative, so we know that this gives us f prime of 0 is going to be negative. So that means in region number 1, okay, we'll just go ahead and put the numbers in here. So for region number 2, we're going to put in +1, since +1 is between 0 and 4. Okay, and then in region number 3, we got 4 through 6, so we can put in, let's say, 5. And then in region number 4, we can put in 7. Okay, so let's just go ahead and just copy this so we can see what our signs are going to look like for each one. So we know that it's negative in the first one, so we know that it's going to be f prime of x is going to be less than 0, so we know it's decreasing. Okay, in region number 2, we let x equal +1, and we got a positive result. So that means f prime of x is going to be greater than 0, so we know it's increasing there. Okay, in region number 3, we let x equal 5, and we got a negative result. So therefore, f prime of x is going to be less than 0. So therefore, it's decreasing in that interval. And then in region number 4, we let x equal 7, and we also got a negative result there. And so therefore, f prime of x is going to be less than 0. And so we know it's decreasing there as well. Okay. And so now that we have those numbers, okay, now what we want to do is we want to be able to then determine, okay, what are the local extreme values. So we're going to use the first derivative test. So remember what the first derivative test tells us, that if f prime changes from positive to negative at c, then f has a local maximum at c. If the first derivative changes from negative to positive at c, then f has a local minimum at c. And if f prime does not change sign at c, therefore there is no local max or local minimum at c. So let's take a look at the first one. It's going from negative to positive. Okay, so the point 0 represents a negative to positive. So for the critical point 0, okay, we know it's going from negative to positive. And so now we want to evaluate this at f of 0. Okay, so let's go ahead and use Desmos again, and let's create another table here. Okay, and we have our function, which is, since it's x2, we're going to call it x2, and that's to the power of 2/3. And then that was times 6 minus x, and that was to the power of 1/3. Okay, so if we put in 0, oops, got to make sure we put that 2 there, then we get 0. So that means f of 0 is equal to 0. So that means we have a local minimum at 0, 0. Okay, so can we take a look at the critical number 4? So if we take a look at the critical number 4, it's going from a positive to a negative. So this one's going to a positive to a negative. So we want to find f of 4. Okay, so let's go ahead and plug that into our calculator. So if we put in 4, we get 3.1748021. So let's put 3.17. Okay, so this tells us that since it's going from a positive to a negative, that this represents a local max. So this is at 4 and then 3.17. Okay, so what about the critical number 6? Well, the sign doesn't change. It goes from negative to negative. So therefore, since it doesn't change, there is, and I'll write that out here, it goes from a negative to a negative. So no change, which means no local max or minimum. Okay. All right, now let's go ahead and move a little further here. Now we want to look at the expression for the second derivative. So I'm going to continue this on another example.